एवरीवन, आज जो मेरा टॉपिक है बेसिकली माइक्रोसॉफ्ट कंपनी ने मेजरोना वन चिप पे क्वांटम का आविष्कार किया है। तो उसके बारे में आज मैं आपको दिखाऊंगा, क्योंकि बहुत सारे पेपर में बहुत तरह की बातें आई हैं। मैं आपको हर पेपर के बारे में आपको बताऊंगा कि कौन से पेपर्स ने क्या लिखा है। एक्चुअली ये बहुत अच्छी आविष्कार हुई है। तो चलिए मैं आपको दिखाता हूँ। यहाँ पर एक पेपर लिखा है कि माइक्रोसॉफ्ट की चिप सभी कंप्यूटरों में काम करेगी अकेले। देखिए लिखा हुआ है कि आईटी कंपनी माइक्रोसॉफ्ट ने गुरुवार को अपनी पहली क्वांटम कंप्यूटिंग चिप मैजरोना वन लॉन्च की। यह टोपोलॉजिकल और आर्किटेक्चर द्वारा संचालित दुनिया का पहला क्वांटम चिप होगा, जिसके बारे में दावा किया जा रहा है कि यह दुनिया के सभी कंप्यूटरों में काम अकेले करने में सक्षम होगी। माइक्रोसॉफ्ट के सीईओ सत्य नडेला ने कहा कि 20 साल की खोज के बाद माइक्रोसॉफ्ट ने आखिरकार ऐसा प्रोडक्ट तैयार किया जो पूरी तरह नया है। यह ऐसी चिप है जो हथेली में फिट हो सकती है और उन समस्याओं को भी हल करने में सक्षम है जिन्हें आप पृथ्वी पर मौजूद सभी कंप्यूटर मिलकर भी हल नहीं कर सकते हैं। ये एडवांस रिसर्च करने में, आपका वेदर फोरकास्टिंग करने में, आपके जो साइंटिफिक वर्क करने के लिए, मेडिकल फील्ड में काम करने के लिए, ट्रैफिक कंट्रोल में काम करने के लिए ये काफ़ी स्टिक आपका इंफॉर्मेशन देगा जो सुपर कंप्यूटर्स के चिप नहीं काम कर पाएंगे। ये आपका क्वांटम चिप आपका क्यूबिट के रूप में काम करेगा। तो चलिए इसके बारे में आपको पूरी दुनिया में बहुत सारे इंफॉर्मेशन से आए हैं, मैं उनको आपको वन बाय वन दिखाता हूं जिससे आपको समझ में आ जाएगा। टीवी भारत ने बोला कि माइक्रोसॉफ्ट ने लॉन्च किया मेजरॉन वन, जानी दुनिया के पहले क्वांटम चिप की खास बातें। वो बता रहा है कि आपका मेजरॉन वन दुनिया का पहला क्वांटम चिप लॉन्च किया जो आपका टोपोलॉजिकल स्कोर आर्किटेक्चर की मदद से चलता है। माइक्रोसॉफ्ट ने यह भी बताया कि ये आपका जो बना हुआ है इसमें आपके खास तरह के मटेरियल्स का यूज हुआ है जिसका ये काफ़ी आपका लंबा टाइम तक काम करेगा। ये बताया गया है इसमें आपके कि ये जो मेजरोना वन जो क्वांटम चिप होंगे वो आपका टोपो कंडक्टर का इस्तेमाल किया गया है। टोपो कंडक्टर का इस्तेमाल किया गया है और ये स्मॉलेस्ट चिप है और ये जो काम करता है वो क्यूबिट वाले प्रोसेसेस में काम करता है। ये आप देखेंगे, मैं माइक्रोसॉफ्ट कंपनी के जो वेबसाइट्स हैं उनके एक वीडियो क्लिप है, उस वीडियो क्लिप को मैं जब दिखाऊंगा तो आपको आसानी से ये समझ में आ जाएगा, क्योंकि ये बहुत एडवांस रिसर्च हुआ है और इसके बारे में मैंने सोचा कि अपने व्यूवर्स को ये बातें बताया जाए, क्योंकि कंप्यूटर की दुनिया में बहुत आपके एडवांस काम हो रहे हैं। आज आप देख रहे हो जो दुनिया में एआई का काम हो रहा है, तो एआई का और एडवांस फीचर्स इसमें काम करने में काफ़ी आपका मदद पहुंचाएगा। तो चलिए मैं आपको माइक्रोसॉफ्ट कंपनी का जो वीडियो क्लिप है उसको मैं आपको दिखाता हूं जिससे आपको समझने में आपको आसान हो जाएंगे। तो चलिए मैं आपको समय गलत नहीं करते हुए मैं आपको दिखा रहा हूँ। मैं आपको दिखा रहा हूँ, देखेंगे। देखिए स्टार्ट मैंने कर दिया है।
Now is one of our longest running research projects. Our team at Microsoft has been able to take a subatomic particle that has only been theorized until now and not only observe it, but control it, creating an entirely new material and a new architecture for quantum computing. One that can scale to millions of qubits on a single chip.
This is not a work of science, it's a work of science and art.
I gotta be honest, some of these ideas are a little science fiction sounding.
It will solve problems unsolvable by the combined power of all the world's compute today, and promises to revolutionize fields such as medicine, material science, and our understanding of the natural world. Our first quantum processor based on this architecture is the Majorana 1. I've always been fascinated with puzzles and challenges and a mixture of mathematics and computers. And so when I learned that there was this type of computer that didn't exist yet but could solve problems that we couldn't solve with our digital, all of the computers we had, I was just fascinated. I wanted to learn, well, how can I help that computer be built?
Over the years, I ran into problems that I could not solve on the most powerful computers. But then over time, I realized, hey, I could solve that if I had a quantum computer. A laptop can solve a problem of 10 electrons. A supercomputer can solve a problem of 20 electrons. But no classical computer in the world can exactly solve the behavior of 30 or 40 or 50 electrons.
The number 30, 40, 50 electrons, those numbers are seemingly small, but require up to lifetime in the universe timescales to solve with all of the world's computers operating together. That's until you have a scaled quantum computer that can solve these problems efficiently.
These calculations are so complicated that then if the classical computer was as big as this entire planet, it would still not be able to compute it, just to give you a construct of scale. And a quantum computer can do it, and can do it very, very well.
At the core of a quantum computer are these qubits. Qubits are like our classical bits, right? These are essentially zeros and ones in a transistor. And we need the analog of that in quantum computing. The analog is a qubit, a quantum bit, that serves as that core information unit. It's where we store the information and then we process on those qubits to create computation and ultimately, get solutions back out. Now, there's many different ways, right, to create a qubit. The reason quantum computing has been so slow to progress is that the industry has been struggling with problems making qubits reliable and resistant to noise. Progress has been incremental.
The challenge is qubits are actually pretty delicate in general, so you need underlying qubits that are really stable. But you don't want that to come at a cost, because you don't want your underlying qubits to be really big. That's one way to make it more stable, is have them really big. But if they're really big and you're still going to need many of them, then how are you going to fit them all into your system? You don't want to deal with something the size of a warehouse. Then the second thing is you don't want the qubits end up being slow, right? Because if the price you pay for getting something stable is you have to go really slowly, then a computation that might take you a month ends up taking you a decade, and then it's not useful. People in the early days of computation used vacuum tubes, and then that technology, actually you could build very good computers with it, and then the transistor was invented, and the earliest transistors weren't necessarily that great, but it became clearer over time as the transistor developed and the integrated circuit developed that this was going to be the technology of the future. In that spirit, that the first generation of qubits may not be what gets us to the next stage where we can really solve the kind of problems I was mentioning that are really important. And so we might need to invent a material and therefore a quantum processing unit that has the right properties. So for us, we want something that has some built-in level of error protection. And a lot of those ideas actually were explored in the context of software, of quantum error correcting codes, but you can actually build a lot of those ideas into hardware.
So the way you design that qubit matters. We see the states of matter every day. Solids keep their shape, liquids vary but keep their volume, gases expand to fill the space they're in, all defined ultimately by how their atoms behave. But what if there were more? What if, under the right conditions, you could engineer more? States that have only ever been theorized, that would change how subatomic particles actually behave? 100 years ago, mathematicians predicted one such new state of matter, the topological state. And since then, researchers have been looking for a very specific, very useful quasi-particle within it, the Majorana particle. Last year, we were able to observe it for the first time. And this year, we're able to control it and use its unique properties to build a topoconductor, a new type of semiconductor that operates also as a superconductor. With this material, we can build a whole new foundational architecture for our quantum computers, a topological core, allowing us to scale to not tens or hundreds of qubits on a chip, but millions, all in the palm of your hand.
Majorana's theory showed that mathematically it's possible to have a particle that is its own antiparticle. That means you can take two of these particles and you bring them together, and they could annihilate and there's nothing left. Or you could take two particles and you bring them together and you just have two particles. Sometimes it's nothing, the zero state, and sometimes it's the electron, the one state.
So it really has taken quite some thinking, right? Some time to design a device, design a chip that can enable measurement of this literally elusive particle. We've designed a chip that is able to measure the presence of Majorana. Majorana allows us to create a topological qubit. A topological qubit is reliable, small, and controllable. This solves the noise problem that creates errors in qubits. Now that we have these topological qubits, we're able to build an entirely new quantum architecture, the topological core, which can scale to 1 million topological qubits on a tiny chip.
Every single atom in this chip is placed purposefully. It is constructed from ground up. It is entirely a new state of matter. Think of us as building the picture by painting it atom by atom. In a regular chip, the computation is done using electrons. We don't use electrons for compute. We use Majoranas for compute. It's an entirely new particle. It's half electron.
When we look at the design of this chip, right, first of all, you can fit so much on just a small form factor, right? This chip can store over 1 million qubits, right? Over 1 million can fit on just this small form factor. In addition, we don't want to wait centuries or millennia for a solution. And so this chip also offers the right speed to get solutions from the chip in a reasonable, efficient, amount of time. That's the beauty in this qubit design, the topological qubit. It has the right size, the right speed, and the right type of controllability. And all of that together means that it has an ability to scale like no other.
The way the system that we are constructing works is you have the quantum accelerator, you have a classical machine that works with it and controls it, and then you have the application that essentially goes between classical and quantum depending on which problem it's trying to solve. Once the computations are done, the results are resynthesized on the classical side and produced back to the user as one complete answer. Where the quantum machine shines, it is able to do simulations, particularly in chemistry and materials, that are extremely accurate as an actual wet lab experiment. Imagine a world where a scientist computes the material that they want, and they compute it to the accuracy that it's first time right. So when you walk into a lab, you don't need to experiment anymore. Imagine a battery that you charge it once and you never have to worry about discharging.
What can you do with 1 million qubits? In the last few years, there's an explosion of artificial intelligence, right? Co-pilots. And what's so inspiring about a quantum computer is that with a quantum computer augmenting the AI capability, it can help more, drive even more discovery.
What makes me excited about quantum computing is that it will give us the tool to tackle many of these challenges at the fundamental level by creating new chemicals, new drugs, new enzymes for food production.
Honestly, it's kind of mind-blowing right now because this is something we've thought about for a while, years or more.
We call the ages of mankind by materials. We've talked about the Stone Age, we've talked about the Bronze Age and the Iron Age, the Steel Age, the Silicon Age. Materials define our culture, define our mankind, define our progress. Thus, what could be more powerful than having a machine that can let you radically change the way we work with materials.
Our leadership has been working on this program for the last 17 years. It is the longest running research program in the company. And after 17 years, when we are showcasing our results, we are showcasing results that are not just incredible, they're real. They are real because they will fundamentally redefine how the next stage of the quantum journey takes place.
We're at the cusp of a quantum age, and Majorana 1 is just the beginning.
तो मैंने आपको दिखाया ये आपके माइक्रोसॉफ्ट कंपनी के द्वारा जो प्रोवाइड की गई थी, जो आपके जो आविष्कार हुए हैं उसके बारे में। और मैंने ये दिखाने की कोशिश इसलिए की कि मैंने देखा कि हर पेपर में हर तरह की बातें की गई है आपके माइक्रोसॉफ्ट के जो मेजरोना आपके जो प्रोसेसर की जो आविष्कार हुआ है। तो मैंने सोचा कि इसके बारे में वीडियो बनानी चाहिए और बताना चाहिए सभी को, क्योंकि कंप्यूटर फील्ड एक ऐसी दुनिया है, इसमें आपके आविष्कार होते रहते हैं। कंप्यूटर की दुनिया में स्पीड का बहुत महत्व होता है, क्योंकि आपको पता होना चाहिए आज के डेट में जो एआई काम करता है उसमें बहुत आपके फास्ट कैलकुलेशंस होते हैं, वो साइंटिफिक रिसर्च करके सारा कुछ देता है। ये आपके जो माइक्रोसॉफ्ट चिप जो आपका मेजरोना जो है वो क्यूबिट्स पर काम करता है। और मैंने आपको वो वीडियो क्लिप दिखाया जो माइक्रोसॉफ्ट कंपनी के द्वारा प्रोवाइड की गई थी, और मैंने ये बताने की कोशिश की है कि आज के डेट में माइक्रोसॉफ्ट कंपनी ने मेजरोना 1 लॉन्च की। बेसिकली ये 20 साल से काम कर रहे थे, इनकी कंपनी के ऑर्गेनाइजेशंस मेंबर जो साइंटिस्ट थे वो काम कर रहे थे, तो इनको सफलता मिली है और ये क्वांटम कंप्यूटर्स के रूप में काम करेंगे और कीबोर्ड्स के रूप में काम करेंगे। जो भी हमारे साइंटिफिक वर्क आज जो नहीं हो पा रहे थे हाई स्टैंडर्ड का, बहुत एडवांस स्टैंडर्ड का, जैसे रिसर्च में काम आएंगे, आपके वेदर फोरकास्टिंग्स में एक्यूरेट इन्फॉर्मेशन मिलेंगे, जो अर्थक्वेक आते हैं उसके भी कैलकुलेशंस करने की संभावना होगी। तो ये आपका एक छोटा सा मतलब इन्फॉर्मेशंस था जो माइक्रोसॉफ्ट ने चिप का जो आविष्कार किया था, जिसका नाम था आपका मेजरोना 1, जो कंप्यूटिंग चिप था। तो मैं आशा करता हूँ कि ये छोटा सा इन्फॉर्मेशन से आपके लिए काफ़ी उपयोगी होगा। तो थैंक्स अ लॉट, थैंक यू।